morning, everybody, and welcome to the second last relativity seminar of this semester. Today we are very glad to have Nikolaos Athanasiou from Ricci, University of Crete, and he's going to talk about the exciting stuff. Not the problem in Einstein-Vlasov.
Thank you so much, Pushkar. First of all, you know how whenever we talk, everybody says how great it is to be speaking. I'm extremely happy to be here again at the CNSA and to be here with you. So indeed, today we're going to be talking about the Einstein-Vlasov system in a large data regime. Before I say anything, everything I'm going to say is based on joint work with Pushkar Mondal. Okay, so a skeleton of the talk will be like this. I will spend a few slides on the introduction and motivation of the things that we're going to be talking about. We will discuss the setup, and then we will discuss a little bit about Vlasov and how it goes, essentially. Okay, so our topic is on the Einstein equation of general relativity, first introduced by Einstein on November 25th, 1915 to the Russian Academy of Sciences. The general theory of relativity says that space-time is a four-dimensional manifold M equal to the Lorentzian metric G. And this metric satisfies the Einstein field equations R mu minus a half R T mu equals T mu, where R mu is the Ricci curvature tensor, R is the scalar curvature of Mg, and T mu denotes the stress energy momentum tensor of the matter field under static. As we all know, this right-hand side contains information on the energy and matter content, and this is a geometrical information, so Einstein was sort of showing it. And initially, the first reactions were that, research followed two broad directions. The first one was experimental verification of the theory, because for a physical theory, if it doesn't match with the observations at all, there's no point in pursuing it further. Secondly, and more of interest perhaps to our talk, was work towards identifying explicit solutions to this Einstein. So this didn't take long to manifest. A month maybe after November, maybe December 1915, Karl Schwarzschild wrote from, I think, the First World War actually, and gave the first example of a non-trivial, non-Minkowski solution to these Einstein equations. But it was not realized until maybe 17 years later of what exactly was happening, in some sense, in this Schwarzschild metric. So it was first realized by Lemaitre that this Schwarzschild metric contains a non-empty region B with the following features. Feature number one is that once you get inside this region B, any observer that sits in B cannot send a signal outside to an ideal boundary at infinity denoted by I plus the future null infinity. Means that once you're in there, you cannot send a signal outside. And secondly, and equally surprising, every time-like Cornell geodesic that enters the interior of B is future incomplete. It stops after time. In fact, as we know, it stops with a very violent way, as we know. So the first reaction of mathematicians and physicists looking at this was that these pathologies should be probably non-generic, and that in general solutions to the Einstein equations, whatever that means, because, mind you, an initial value formulation has not yet been set up, such pathologies should not arise. In fact, as we can see, the Schwarzschild metric contains a lot of symmetry, in case we can see. So it was conjectured or hoped for, I don't know, that these were artifacts of the symmetry. Okay. So in fact, maybe 17 years or so again after Lemaitre, for 20 years, it was understood that general relativity can be used as a dynamical theory. Okay? So you can have evolution of initial data on Cauchy hypersurface. And the first step towards understanding this was made by Jacobi, who was at Princeton in 1952, proving a local existence result for sufficiently smooth data. And the corresponding thing to the maximal time of existence of the system, the existence of a maximal global hyperbolic development, maximal solution to G, uniquely determined by some initial conditions S0, which is dimension manifold, and the metric minus G, and the tensor K for the Einstein equations, satisfying the constraint equations. Okay. That happened in 1969. Important to our talk is also the formulation of the characteristic initial value problem by Alan Benthal in 1990, in which we basically impose data on two cones, and this is the approach that has been adopted, more or less, for most, not all, but most of the trapped surface formation results later on. So, the person who spectacularly falsified all hopes of black holes of being pathologies and accidents was Sir Roger Penrose, who was in 2020 co-awarded a Nobel Prize in Physics, quote, for the discovery that black hole formation is a robust prediction of the general theorem. Okay. The way Penrose achieved this was by introducing the pivotal notion of a trapped surface. Given a 3 + 1 dimensional Lorentzian manifold M, G, a closed space-like two-surface S is called trapped if the following two fundamental forms have everywhere pointwise negative expansion. Meaning you look at the traces here, trace chi bar. The trace chi bar is usually the easy part, okay, because it's negative. Proving trace chi bar negative pointwise is dynamically difficult thing. Where, of course, here, D denotes the Levi-Civita connection of T. These are a null basis, L and L bar denote a null basis of the complement of TPS in TPM. Okay, so two-dimensional. And X and Y are arbitrary S tangent tensor fields. Geometrically, these traces denote the infinitesimal change in area for these spheres. Okay. So this is basically saying, like, in future directions, this area tends to. And the theorem that was showed, the famous completeness theorem, was that if you have a global hyperbolic space-time, say arising from the Cauchy problem, with a non-compact Cauchy hypersurface, and if M satisfies some very reasonable energy conditions, then if I contain a closed trapped surface, then I impute causal. And this is in some sense how you understand a singularity in the first instance by geodesic incompleteness. Okay? Of course, as we know, singularities can come in all shapes and sizes and forms, but that is a different area, huge area of study. Okay. But as often happens science. You solve one question and 10 more come up. Okay, so the point was that the existence of a trapped surface in the space-time was something very strong to begin with. In fact, in early days, the only way to know for sure that the trapped surface exists is to impose it on the initial data. So it was natural to ask whether trapped surfaces are themselves dynamical objects, or whether in this, Cauchy problem framework or characteristic initial value framework can be derived in evolution of data which do not contain. So the first such existence result, albeit elliptic and on the assumed and on the initial surface, is due to Shane Yao, in which they impose basically a smart notion of radius, which, if large enough, shows that you have a trapped surface in your initial. Dynamically, the story begins with Dimitri Christodoulou. In fact, the problem of trapped surface formation was given to him by his advisor, J.A. Wheeler, at Princeton. And it was basically about the complete absence of symmetry. So it was absolutely a very difficult problem for a doctoral thesis. And in fact, Christodoulou has often said that it's a good thing I left it for a while, otherwise it would take me 40 years to get my PhD. But you can sort of look at the next best thing, okay? And by looking at the next best thing, Christodoulou was able to absolutely kill the problem. So, in a series of papers by Christodoulou, he looked at the gravitational collapse of a scalar field. Okay? So this is the next best thing you can have, because in Schwarzschild you have this Ricci result. Okay, so he managed to prove, first of all, prove that there are initial data that form a trapped surface. And in fact, your data on your incoming cone can be as bad as you want. In fact, this is important later on. So, data that have form a trapped surface. Data that give rise to naked singularities, and proof that these data that give rise to singularities are somehow the dimension one in the modular isolation of this data. And hence, unstable, naked singularities are unstable. So this was a huge success of Christodoulou in its entirety, if you want. But the problem in the absence of symmetry remained persistent. Okay? And in fact, it was only in 2008 that the breakthrough came in the absence of symmetry for the vacuum equations using something that came to be known as the delta short pulse method. Itself, the delta short pulse method was inspired by Christodoulou for a similar problem, that of shock formation, okay? And used also in this transformation. What is the difficult thing about, philosophically about getting such a result? Philosophically, precisely because of the monumental proof of Christodoulou-Kleinemann stability of Minkowski, if you hope to see something bad happening, okay, you better be away from trivial data in some well-meant sense. But at the same time, if you're too far away from trivial data, and your data is super bad, then you don't even have a hope of proving existence for time long enough for the trapped surface to even have a chance to form. So somehow you needed to bargain, essentially, and guess a hierarchy that gets propagated upon evolution. Okay? So this is what Christodoulou here managed to do. It was a great feat, by all means. Soon after came the work of Kleinemann-Rodniansky in 2009, where they used a slightly different scaling of initial data and managed to get a trapped surface formation result. Christodoulou needed 2 derivatives of curvature to prove his result. They needed 1 derivative of curvature. But what for me is the most important gain from this is that the 600-page document was reduced to 100 pages or something. And it facilitated, a lot of things. Okay, so really, in this delta short pulse method incident, or framework if you want, Christodoulou manages to build a trapped surface of size 1 relative to delta. Okay. However, the question remained, what is sort of an optimal size of trapped surface that I can get, in this experiment? Okay. So this goes to the work of Van Luck in 2014 for a scale critical trapped surface formation criterion in a finite region. Okay. So now Anne and Luck were able to build, given this delta framework, a trapped surface of size delta alpha, where alpha is a large constant like a half. And crucially also to our work and subsequent work is the work of Anne, where he proves a scale critical formation criterion for the Einstein vacuum equations by introducing this pivotal notion of signature for decay rates, which allows one to translate the problem from 0 to delta, 0 to 1. There's sort of different scaling, as we're going to see. And moreover, he improves it to just maybe 50 to 60 pages, the whole argument. Okay. So then also related, I guess, to this is my work with Singa and on the Einstein-Maxwell system, getting a similar job to the theorem. Also the work with Huskar and Xin Yao on the Einstein-Young-Mills system. Another recent work, actually one for which Dr. Chen gave a talk maybe 2 or 3 weeks earlier here, was trap surface formation under a geodesic foliation, so not a double number foliation. And I could not help but mentioning the works of Jonathan Luke and Igor Rodnianski on impulsive gravitational waves, in which they managed to give energy estimates avoiding alpha and alpha bar. And moreover, they do have a trap surface formation result in their papers. Okay? And finally, I don't want to bore you maybe too much. Philosophically, why is the trap surface formation interesting? We have, physical black holes, the things we have photographed in the Event Horizon Telescope, and we have mathematical black holes as we come to understand them. Of course, as mathematicians, our hope is to predict things that the physicists either should try to see or cannot see inside the interior of the black hole. So, there are 3 tests of, reality of, black holes. Okay, the first one is rigidity. Can we characterize all vacuum black holes? Are there domains of other communication of all regular, stationary, four-dimensional vacuum black holes? Isometrically diffeomorphic to those solution. Anyway, stability. Are black hole solutions stable under perturbations of initial data that gives rise to them? Or if I throw a pebble in the initial data, I will suddenly get an evaporation of the black hole. If black holes are meant to be physical, they better be stable, as it is mentioned. And finally, the formation argument. If black holes are physically manifestable, then they better form from a time when they did not exist. This is sort of captured by the notion of dynamical black hole formation. So this is why this problem is in general of interest. Okay. So for the Einstein-Vlasov system, contrary to the Einstein vacuum or Einstein-Maxwell systems, the Einstein-Vlasov system exhibits non-trivial dynamics even in spherical symmetry. More importantly, a pivotal result was given by Martin Taylor, published in 2017, namely the stability of Minkowski space as a solution to the Einstein massless Vlasov system, which is also of importance and relevance to our own work. Later on, Martin Taylor and Hans Littleblatt obtained the same result, but for the massive Vlasov system. And instead of a double null foliation, they use a harmonic coordinate gauge. And now, the question that was sort of improved was that initially F is assumed to have compact support in the space and momentum variables. So later on, Feynman, Judieu, and Ricci extend this result and allow for non-compact support in the momentum variables initially for F, which was then further improved for the massless case by Leo Bicorn, David Feynman, Jeremy Judieu, Jackson Ricci, and Maximilian Thaler. No compact support assumptions on the initial data of the Vlasov field in either space or momentum variables. So these were preceded by important works on spherical symmetry, Ryan Rental in '92, and Afermos Rental in '04. Of particular interest, as it turns out to us, was this paper of Ryan Rental. We will explain more. For Ryan Rental, it was like small data, global existence of spherically symmetric Vlasov matter. And for the Afermos Rental was that the sort of first singularity should emanate for the center. It had implications for it was even a proof of a trap surface formation result somehow already. Our framework is a framework of double null relations. Okay? So the spacetime we construct in the present work is covered by a double null relation given by three-dimensional incoming null hypersurfaces h bar u bar prime for 0 u bar prime less than 1, which is like this. Outgoing null hypersurfaces hu go like this. And their pairwise intersections hu u bar. So their intersections are two spheres, okay? Indexed by u and u bar. Throughout, okay, we will be working with normalized vectors, okay? This is standard such that 0, e3, e4 is -2, and the null lapse function. We construct a coordinate system in which the metric takes the following form. And this setup then, we impose the Einstein-Vlasov system on this. So, the equations governing the evolution of the Einstein-Vlasov system are r mu mu minus a half r g mu mu equals t mu mu of f. Well, I will explain here what the energy momentum tensor is of this Vlasov matter. In fact, this is a massless Vlasov equation. And the Vlasov equation itself is x of f is equal to 0, where x is a vector field. Okay. On Tm called the geodesic spray. Essentially what this says is that f, which naturally lives on a subset of Tm, is propagated, okay, along the geodesic flow on Tm. So the unknowns, okay, are a Lorentzian manifold Mg, and the particle density or distribution function, if you want, f, which starts from a subset of Tm and goes into 0 infinity. So it is a non-negative function, essentially. But what is P? Okay? P is a subset of the tangent bundle called the mass shell. In our case, it is given by this equation here, okay? Which precisely manifests the massless condition. Okay, so the function f of x comma p, what does it represent in physical terms? It represents the density of the matter at the point x with a given momentum or velocity p of x. Okay? So, we give some coordinates on the tangent bundle, okay? So xm gives the position, and pm gives essentially the momentum. So pm is sort of the conjugate to xm, okay? So that ultimately xm comma pm denotes the point p mu partial x mu at x, which lives in the tangent bundle, okay? As I mentioned, the mass cell is given by all those x comma p in Tm such that, these are null and future directed. X is a vector field on Tm called the geodesic spray. And moreover, if one assumes restricted coordinates, okay, because of the mass cell condition, I can relate P4 to P1, P2, P3 because of the mass cell condition, as we can see. Okay, so the Vlasov equation on the mass cell, okay, rewrites as p mu partial x mu of f minus gamma hat lambda mu mu p mu b mu partial p bar lambda hat of f, where lambda hat simply means that now I'm running from 1 to 3, not 4. And these p bar are the restricted coordinates on the mass shell. Okay, let's take this form here. So our theorem is as follows. Our theorem is essentially a semi-global existence result for large data for this system, okay? And also the imposition of
P4 now direction.
Sorry?
P4 is at now.
Yeah, P3, P4 is like this, and here the angle. So what you see here more or less for the geometric part is exactly what's happening in already Anne's work for signature of decay rates, okay? And the free data, as we see, are some derivatives of f0, okay? Of course, seven sort of things can be here, but the exact form of these f's will be given in a few slides, okay? But for now, this sort of data. This is how this goes. Okay, so given I greater than 0, there exists a sufficiently large A0 depending on I, such that the following holds. For any A that is below this, above this threshold A0, and with smooth initial data satisfying this sum, okay, A to the minus a half, nabla for M times U infinity nabla I times of chi hat, this is your pre-initial datum, okay, in L infinity is bounded by I. Mini pause here. A is assumed to be large, so this is somehow where the largeness comes into play, that these sort of derivatives are bounded by A to the half, where A is large, control. And on your incoming cone, you have Minkowski initial datum. Okay. So for the Vlasov part itself, the initial distribution function. Sorry? No, it's a different approach to begin with. Okay, so in Christodoulou we see something like this, maybe of size 1 here, which can be here we see some U infinity here, which can go all the way. This is assumed to be very large and negative. It can go up to minus A over 4, where A is large. Okay? So in principle, for example, in the unlooped work, okay, there were some 3 parameters. There was delta, A, and B. And then the condition was delta A to the half B is less than 1. And if B is equal to A to the half, let's say that delta should be like 1 over A. Okay? But in general, you can think independently here. Okay, so moreover, this is how initially the P4s behave for some fixed constants independent of U0. Then the Einstein-Vlasov system admits a unique smooth solution in the region U infinity less or equal than U less or equal than minus A over 4, and 0 less or equal than U bar less or equal than 1. If in addition the initial data also satisfy an isotropic condition along of integral U infinity squared chi hat 0 squared plus T for 4 0 squared, okay, greater or equal than A, which is, T for 4 is prescribed by F0 here. Uniformly for every direction along U equals U infinity, then the spacetime has a trapped surface at S minus A over 4, comma. There is no restriction as to why we would not apply Luke Kleiner-Macrobianski's anisotropic trapped transformation. It's just we don't do it. Okay, so the Einstein-Vlasov system in a double null foliation works as follows. We work with the system R mu minus a half R G mu equals this stress energy momentum tensor of the Vlasov matter. Here, P3 is something non-negative, okay? And the PAs can be anywhere real values, okay? The PAs, the angular momentum. Integral F P mu P nu, the volume form essentially of the mass on this thing. Root that G over P3, dP1, dP2, dP3. This is sort of the restriction on a given X of the mass cell, which is the definition. So introduce null tetrads EA, EB, 3, 4, okay, where A and B is 1, 2, and require that say they are somehow orthonormal in the Lorentzian sense. Okay. And for the Weil curvature, we do something very, very mainstream. Okay, so we define the null Weil curvature components. W EA for EB 4, alpha bar is EA 3 BE3, beta and beta bar are the known counterparts. Rho and sigma are also the well-known decomposition of the Weil tensor. Okay, and in the same frame we have the Ricci coefficients: chi AB, chi bar AB, eta bar, omega bar, and the torsion. And of course, this is the first time I explained what the mass-cell relation looks like in this framework. It relates P4 to the angular derivatives in P3 by saying G of P comma P equals 0. So under this frame, G slash alpha beta PAPB minus 434 is equal to 0. And of course, now the Einstein equations break down into a system of structural equations, okay, for the Ricci coefficients, and some constraint equations, together with the Bianchi equations, which are the heart of the matter, okay? So these are also, okay, the form that these equations take. And the Bianchi equations expressed in a double null gates take also the following form: nabla 3 alpha plus h raised chi bar alpha equals this expression over here, where crucially, because I'm not in vacuum, I have these non-trivial derivatives of the matter field. As it happens here, the RAB is TAB. So R mu nu is equal to T mu nu, because it's massless. Okay. So anyway, this is what these things look like, essentially. Okay, our approach will be also standard in terms of an energy argument. We will be integrating in Bianchi pairs. But the point is already that here you see that matter is of one derivative higher than curvature. So if you want estimates on n derivatives of curvature, you better have estimates on n plus 1 derivatives of the Vlasov matter. Now, crucially, how does the structure of the proof go? All our estimates are carried out in this scale invariant framework, okay, which was introduced by Xin-Yang An, which is the following. If I have an arbitrary brain freeze, let's go, curvature, Ricci component, we assign a number S2 called the signature for decay rates to it. Essentially, we are awarding and not awarding points according to how many times this thing appears. And by the way, the fact that something like this can hold and be uniform in all Ricci and all curvature has always amazed me. That you can set up, hierarchies just by counting how many times it's here. So 0 times n for 5, okay? 1 times every time an angular component comes into the definition, and 1 times n3 5 minus 1. Okay? So for example, for this chi here, if chi is defined as just d alpha e4 eb, this will be a half plus a half minus 1, right? So 0, etc. So here's the number of times each j appears in the definition of phi. For such phi, we define the scale invariant norms. The L infinity scale invariant norm is, what do we give? A to the minus s to phi, u to the 2 s to phi plus 1 times the regularity. Phi in L2 is a to the minus s to phi, u to the 2s to phi times phi in L2. Phi L1 is equal to this, okay, accordingly. And moreover, but before I continue, let me sort of tell you what this, philosophically, what the scale invariant norms do. What they do is that they approximately propagate the size of the data. So, if this is a regular, so to speak, Ricci coefficient or curvature component, I expect its L infinity norm to be like a to the s to phi over u to the s to 2s to phi, okay, in decay. Moreover, we define norms along the outgoing null hypersurfaces, which are going to be used in the energy argument, and norms in the incoming direction. Okay, integral of a over 2 bar squared, phi L2 scale squared du prime. But there is also the Vlasov part, okay? So the Vlasov part, which is basically the components of the energy momentum tensor, T44, T43, T33, T43, and T. Here, T means, for example, TAB, right? And this means T3A, T3B. We assign the signature so that there is conservation of signature throughout the structure and Bianchi equations. What this means is the following. At first, there is a conservation and balance of signatures along every transport, every constraint, every Bianchi equation, and for the Vlasov matter wherever it appears. So S2 of some non-linearity here is the sum of the signatures. So there's balance in every equation. That's number one. Number two is that the Einstein-Vlasov equations are a coupled system of many geometric quantities. And the signature for decay rates, what it does is that it allows one to give norms such that upon evolution, as I mentioned, most of these quantities are bounded by 1. These ones, essentially. With the exception of a few anomalous terms which naturally arise. But most importantly, perhaps, this also goes back to Christoph's maybe remark a little bit, which is that the scale invariant Holder inequality here, phi 1 times f2 in L2 scale, buys a 1 over u bar. And because u bar is now large, this gives a smallest factor, even though the same happens, of course, in L1. So here, okay, you have a scale invariant Holder inequality in L1 and L2. But contrast this to, say, Kleiner-Bianchi's delta scaled norms, okay, where a nonlinearity in L2 is bounded by delta to the half, phi 1 in L infinity, phi 2 in this L2 scale, where now delta is small. Okay. And the point, this is exactly what helps us go through the entirety of the bootstrap arguments. Okay, so this game in smallest is crucial to running the bootstrap arguments for semi-global existence. All right, I will now focus my attention on estimates for basically T, okay, the components of the energy momentum tensor. Why do we care about the components of the energy momentum tensor? Essentially, this R for A here, one might as well write T for A, one might as well write T for 4, etc. Okay? So to close an energy argument, I need control on the energy momentum tensor components, okay, in an energy argument. Analogously to whatever is needed for the Gervarsson components, but in one derivative higher. How do we do this? Assuming some estimates for derivatives of f, okay, I can translate them to estimates for derivatives of t. Of course, derivatives of t will lie, let's say, in Tm, okay, but derivatives of L will lie in Tm. Okay, so there's a translation between those. Our ultimate goal is to translate the energy momentum tensor components. This is done by controlling f and its derivatives. So, assume, okay, that D belongs to mod U nabla 3, nabla 4, and nabla, okay, standard differential operators on M. Consider the corresponding operators mathcal D if you want, U, E3, E4, E alpha, lifted somehow, okay, as sections of TTM. Then, derivatives of the energy momentum tensor translate to the energy momentum tensor applied to set derivatives of f, plus some error terms which are always controllable. Okay. So the point comes down to getting estimates for derivatives of f. Now, we begin by the simplest thing, which is zero order estimates. Okay. Somehow we need decay at zero order for the components of the energy momentum tensor. This decay is not going to come from f. Why? Because xf is 0, it's propagated along the geodesic flow. So the supremum, okay, in the mass shell of f is the supremum restricted to the initial surface. It's propagated. But the decay of t as, u changes here, okay, is obtained by the decay of the support of f in the mass shell, the momentum. Okay, so let gamma denote let gamma denote a null geodesic emanating from the initial surface, such that gamma 0 and gamma dot of 0 are part of the support. At any time s, I can write the tangent vector as PA EA plus P3 E3 plus P4 E4. I get bounds on the momentum at first instance. Okay, so P3 scales like a constant. Okay. P4 decays like u to the minus 2, and so does P alpha. And in some sense, this is the only hierarchy that you can propagate. Why? Because something geometric must happen. Algebraic. You'll see what I mean. So P3 like constant, P4 like u to the minus 2, Pa like u to the minus 2. Contrast this with, let's say, the work of Martin Taylor. Just because our frameworks are different here, okay, I'm sort of going this way, but Taylor is going this way, right? So in Taylor, for example, P4 is the constant one. This guy is, P3 is like u to the minus 2, and Pa is this. Okay, there's this sort of, respect happening here. But how is this proved? You use the geodesic equations, P4 dot is minus a quarter trace chi bar, etc. I'm not going to say the whole thing. P3 dot, you get some expression, okay, involving the p's, involving everything. So it's a bootstrap argument, essentially, okay? So you bootstrap on the p's and you bootstrap on the... Okay. So P dot A of S is, again, like this. Notice there is nabla beta here, which is going to be important later on. Together, okay, with control on all the Ricci coefficients, beta and gamma, we obtain the desired bound just by using the geodesic equations. So we arrive at equations of the form d of u squared before du is u squared omega squared minus times minus trace chi bar plus 2 over u. The fact that I'm using u squared here is precisely why this 2 over u comes into play. Otherwise, trace chi bar together with this guy and this guy is non-integral. Okay? This is why this needs to be u to the square. Okay? Accordingly, in Taylor, trace chi needs to be minus 2 over u. Okay, so this is the philosophy here, that the appearance of trace chi bar plus 2 over u is crucial, and it is what makes the right-hand side integrable. So ultimately, we have some decay for P4, P3, and Pa. This translates to decay in the momentum variables. Let's say, for example, T44, I don't know if I'm visible, yeah, is the integral f, this is P4, P4, so, I raise it, it becomes like P3, P3, root that G. dp1, dp2, dp3. And now, this root that G is like u squared. Oh. There's a constant here, like 4. Root that G, dp1, dp2, dp3. These guys give you a u to the minus 2 times u to the minus 2, so this gives you a u to the minus 4. This is like the constant, and this is a u squared, so ultimately this behaves like alpha of u squared. Okay, because of f. This is the idea. So that's 0 ohms. To do any sort of calculations here, we need derivatives of f that somehow respect the evolution of the geodesic vector field, the geodesic frame. And since f lives on the mass shell, to estimate derivatives of f, we use vector fields that are sections of the tangent bundle of the tangent bundle, much like the geodesic frame. Now, to create those vector fields, good vector fields, one natural way is to lift vector fields from gamma Tm to gamma Ttm. Okay, so the vertical lifts are as follows. Given a v that is in Txm, its vertical lift is defined to be a vector tangent to a curve that lives on Tm. What is that curve? It's a x, p plus sv. So you vary the momentum direction at s equals 0. For the horizontal lift, slightly more work needs to be done. So first you let C to be a curve on M with, C0 equals X and C star 0 is V. So you extend the P to a vector field along this curve C by parallel transport. And then the horizontal lift is defined to be the tangent vector to the curve on Tn given by this expression here, essentially. So, given the coordinates P1 to P4 on the Txm, which are conjugate to E1, E4, the double null frame on mathcal M, okay, one has a frame for Tm given by E1 to E4, E1 to P4. And now, if V in Txm is written as V mu in mu, okay, what is the vertical lift? The vertical lift is V mu partial V mu. And there's a similar expression, slightly more complicated, for horizontal xp at v, which is v mu in mu minus v mu p mu gamma lambda mi mu partial v lambda. We note that after restricting x to the one codimension one mass shell, massless, the Vlasov equation rewrites as p mu in mu minus gamma lambda mi mu p mu partial p bar lambda. F equals 0, where lambda now goes from 1 to t to 3, and p1, p2, p3 denote the restrictions to p. Okay, now, how do we estimate the first derivatives of f? Let's say what happens in order 1. We discussed order 0. For a vector field that is in the a section of the tangent space of the cell, the following equation holds: xv of f is xvf minus vx, because it's equals 0. The idea is to break this tangent space at the mass shell into a basis of vectors for which the size VIF is sort of controllable nicely. And the vector fields used are the following: horizontally A minus P3 over U bar partial V bar A. These also respect what Taylor does if you want, modified for our purposes. You need to be careful with at some point you need to change P4 to P3 and but this is anyway how these are built. Okay. And now what is the point here? The point here is that we do a bootstrap argument. Okay. Say we want to get these types of derivatives. I want to estimate EAF to be like a constant. U partial U of F to be like a constant. Partial V of F to be like a constant. Okay, so I give a bootstrap assumption V by a large constant, which I can actually allow to be out of A. And what we saw is that this is bounded by initial data. Okay. We do this by estimating, now how do we do this? We estimate the quantities VIF and then translate them back to the F frame. Okay, because the VIs are the natural best candidates for commutation. And now, in preceding works in double null correlation, the way these derivatives were obtained, the control on them, were using Jacobi fields. So in Taylor 16, given a vector on the tangent space of the mass shell, okay, and since f of xp is f of the exponential map at s at x comma p, a slight comment here, this is not the exact exponential map tm to m, this is tm to tm, where the exponential at s at x comma p is, what the geodesic is at position x with momentum p, and you follow it for a fine time s, gamma and gamma dot, okay, tm to tm. So one can show that vf at x comma p is some Jacobi field basically applied to f at x comma p. And the idea is that you let x comma p to go back to the initial hypersurface, your initial data if you want. And this relates a derivative of f at a given point xp to a derivative of f at the initial surface. And if you want, the differential of the exponential map here is what? It's ttm to ttm, okay? This is a Jacobi field. And you estimate the components using the Jacobi equation nabla xj equals rx comma j x. In some sense, this is like taking d squared over ds squared in Taylor, okay? And you somehow need this side to be twice integrable somehow, okay? In order to, it's a matter of integrability. Perhaps more immediately or more obviously, one could hope to obtain estimates for the derivatives of f, just as I explained, just by commuting, if you want, with various vector fields. So as Taylor points out, there is an apparent issue with directly going out of this one. With directly commuting the Vlasov equation with various vector fields and estimating the error terms arising along the geodesic flow. Okay, so we start with the Vlasov equation, which reads x of f equals 0. If v is a vector field, commuting will give x of vf is some error term, where the error term is an error involving terms of the form v of gamma mu lambda. At first glance, okay, so if v is, for example, u horizontally 3, ue3 downstairs is what acts on gamma mu lambda. So at first glance, this seems promising. Okay, you have first derivative if you want of Christopher's symbol, you would expect this to behave like curvature. But as Taylor points out, indeed this doesn't happen for all components. For example, if v involves an angular derivative, okay, then v of gamma beta for a, okay, particular Christoffel symbol, will contain two angular derivatives of the vector field B. Now, itself the vector field, the shift vector field B, if you want shift B, is estimated through an equation of the form nabla 3b is equal to Christoffel plus Christoffel times B. In fact, there is a minus a half trace hair bar here. So it's not, there's a plus half trace hair bar. So, commuting with two angular derivatives, you would see nabla squared gamma, which should leave at first order of differentiability for the curvature and for t. And a similar issue with angular derivatives of the spherical Christoffel symbols also appears, okay, not just in P. In this, project, we propose a way around these difficulties.
What's capital C?
Sorry?
What's capital C?
The curvature. Yeah, sorry, I didn't find it. What is the idea? The idea is the following. We will illustrate the idea by estimating, let's say as an example, x and VA as was originally explained here. Okay, so VA is horizontally A minus P3 over Q partial P bar A. Okay. What do we do? Precisely because in a holonomic basis, in a coordinate basis, it's much easier to estimate the components here, okay? We do this in a non-holonomic base and then translate the control in the F basis, okay? So this is done because in a holonomic basis, the commutator enjoys the simple formula that we see here. And of course, XVAI Ci of F, okay? And now, the XVAI are written like this in this coordinate basis, but they are estimated, they're ordered due to the something, in the F basis, okay? So we will see, for example, some XVA here I behave like order u to the minus 1, but because my F basis is mod u partial u, that becomes order u to the minus 2 in the u partial u basis. So, for the first two components in the C basis, you know, x of what is the big component of VA, delta AB, minus VA of the big component of x. Ultimately, we get an expression like this, gamma beta alpha nu p nu plus p3 over u delta alpha beta plus some good terms. The point is that throughout here, for all these vector fields and all these commutators, you need to be careful because there always exist nice cancellations that create the term that is missing most of the time, which is trace chi bar plus 2 over u. So here, you know, the worst thing that I can have is P3 to have P3 here. Okay, so gamma beta A3 P3. That gives me, you know, chi AB P3, right? So chi hat AB plus a half trace chi bar delta AB P3 plus order to the minus u to the minus 2. So that's this. And now I combine P3 a half trace chi bar plus P3 over u, and that gives me a half P3 delta alpha beta. The nice term appears, and I'm integrable again. Such things happen throughout this commutation for all commutators up to 7 and for all vector fields if you want. Similar cancellations occur for the third and fourth components, but I still haven't addressed the regularity issue. Okay, I have maybe addressed the integrability issue, but not the regularity issue. For the regularity issue, this is perhaps where one can see what the idea is. X comma horizontally a minus P3 over u partial array, the 4 plus beta component is this weird term minus x gamma beta a nu p nu plus horizontally a gamma beta mu p nu p nu minus x P3 over u minus this also. Okay, so you have EA of gamma beta mu nu p nu p nu, but at the same time, coming from here, you have minus E nu gamma beta A nu. And it is precisely differences like this that give you curvature plus, so by itself, this guy cannot be estimated, as Taylor points out. But throughout this commutation, always derivatives appear in combinations that give curvature plus terms on the form Christoffel times Christoffel, which are harmless both in terms of integrability and regularity. Okay. So, importantly, there's also a lot of cancellation happening here. And this is not the only thing. The only thing is that once you write this as curvature plus Ricci times Christoffel times Christoffel, you again need to have a simplification of all this term with the term that is missing. It's like a jigsaw puzzle that matches. So these terms simplified together, the gamma beta mu stays the same here. And you know, when this is gamma C A3 P3, this cancels with P3 over U partial array. Just in the same way that this happened. So this means integrability, but this means regularity. For the terms, this is exactly as I said. This is the the identity that allows all this to happen. In other words, throughout the entire argument, derivatives of Christoffel sequence will always appear in differences that define Riemann curvature components up to terms of the form gamma dot gamma, which are harmless at least in terms of integrability. Now, this was perhaps already hinted on in earlier works. For example, Reiner et al. Had a mistake in their original proof, and they published an erratum 2 years later, in '94. And in the erratum, they said that maybe such an approach can be feasible in spherical symmetry. The idea was already existent in the Fermos rental, perhaps, but this is the first time we see it happen in outside of symmetry, and this observation means that one can avoid if one wishes the use of Jacobi fields or together, and just commute. This is true, more importantly, in any data regime, not just in the large data regime, in the sense that one could envision, if one could envision to just rewrite, with a different technique, stability results. So a few more examples to convince one that this happens throughout all the VIs and all the components, if you want. Again, you get E4 gamma beta mu nu minus E nu gamma theta for nu, and this translates to curvature if you want, plus error terms. And finally, how to obtain larger derivatives if you want, without getting into the details of the energy argument. For higher order derivatives, we obtain a schematic form, not a recurrence form, for x VIN up to VI1 of f. So if mathcal Cij now is the component in the V basis, okay, so x comma Vi is Cij Vj, then we have this expression here for multiple derivatives of f, okay? What are we seeing here, apart from the technicalities? Okay, there are some sounds happening here and there, but the point is that derivatives fall on this mathcal C, and what is mathcal C? Mathcal C is a combination of Ricci, curvature, and P's. Yeah? And then Vn, blah, 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 F. So if we want, let's say, so then again, you do a bootstrap argument here to estimate these derivatives. Now, philosophically, the fact that possibly any number of these V derivatives may fall on the Cij, which contains Ricci, etc., means I need to estimate all derivatives of Ricci coefficient and curvature components for all operators, mod UE3, nabla 4, and nabla. Up to now, in terms of trapped surface formation results, we only obtained estimates for nabla. And finding schematic formula for UE3, nabla 4, and an arbitrary of them was also something we did. So instead of using recursion, we obtain estimates for decay now of Ricci and curvature, which is any of those operators. At the highest level of derivatives, elliptic estimates are required for the Ricci coefficients. Throughout, the hierarchies are propagated, used, given by the signature for decay rates. And of course, once existence has been established, proving formation of trapped surfaces is straightforward. I won't discuss it here. This is what I wanted to say in a nutshell. Thank you. Thank you very much.
All right. Thanks, Nicholas. Do we have any questions from the Zoom? From the audience, from the Zoom audience, from the audience here?
Is there another systematic way of understanding the horizontal rifts and the geodesic spray should always move in good terms, like curvature terms?
In principle, you should expect it, absolutely. There's no...
There should be a theorem, right? Like, so I look at
It is, I'm not saying we have rediscovered it.
No,
but this was not...
I know that it's not done yet.
Not yet.
I think it will be nice
To formulate just such a... independently of any trapped surface formation result. It's pure geometry.
Yes. I mean, I think this would maybe also systematic.
I appreciate that. Yeah, just in the form of a theorem. Yeah, right. Yeah, absolutely. In some sense, you expect
This is what happens, right?
Exactly. This is what happens. The V's may change not in spirit, but in type, depending on the framework of the problem you want. But if they are the right ones, because there are right ones for every problem. Okay. So horizontally A, for example, is not the right one. Horizontally A minus P3 over U bar parts of the bar is the right one, because the bad terms cancel. You do something like this in every framework.
But this has to do with just the...
I agree. Pushkar, do you have any questions? I'm joking.
Anybody else have any questions on Zoom?
I was interested in the bootstrapping assumption you guys made.
That one, there's tons of bootstrap assumptions flying around.
Like, why that one?
What they are actually, yeah. So, okay.
It also shows the main theory.
Yeah, absolutely. Answer your question, okay? Initially, what we do is we obtain estimates for 10 derivatives of Ricci coefficients and 9 derivatives of curvature. Ultimately, we close energy estimates at 10 derivatives of curvature. So you have bootstrap assumptions on the Ricci, curvature, and Vlasov, and you close. Okay? That's one. Then you have also for curvature the same thing, because at one order lower than the energy argument, you may as well treat the Bianchi equations as transport equations, so to speak. Okay? So again, the bootstrap is on Ricci, curvature, and Vlasov. Then you go to the Vlasov part. Okay, you have improved whatever you have improved from the Ricci coefficients, but it also works if you just assume it for a bootstrap. Okay, and you bootstrap on the V and improve the V, the Vlasov. Okay, so then once you have done this, you go and you do estimates for 11 derivatives, the total over derivatives, elliptic estimates, bootstrap on those and close those. Then finally you do estimates for 11 derivatives of F, but now you cannot do this in a limit. You need to integrate over the sphere to get any sort of thing. And finally you have the energy argument where everything has been sort of dealt with now. Okay, so you just go and do a divergence theorem on the space. So it's this like that.
Any questions from the Zoom or the audience? If not,